All right, so we start chapter 4, calculus on surfaces. So we will study differential geometry of surfaces, okay? This theory is basically developed by Gauss, and then Riemann took it and generalized to all dimensions. So we will here consider only surfaces, two-dimensional objects, inter space, but then by Riemann, it was generalized to all dimensions. And generalization of surfaces are called manifolds. And actually, if you do geometry, you need to put a metric on it, and then they are called Riemannian manifolds. But we will not go into them. We will only consider what basically Gauss did. Surfaces, theory of differential geometry of surfaces. Okay, so first section is surfaces in R3. So what's a surface in R3? A surface in R3 is a subset of R3 that looks like R2 locally. So when you are on the surface at a point, if you look around, you will think that it is flat. Okay, it's like R2. More specifically, we have the following definition. We want it look like R2 because, if it is like R2, then you can do calculus, okay? You can differentiate, integrate, and do such things, right? You can do anything you do on R2 on a surface. That's why we want to study objects like this, so that we can do analysis on it. All right, here is the definition. Of course, this is not something very strange, right? People used to think that, the earth was flat for centuries, right? So it's natural to think that, if you're on a surface, it's like R2. So it is not something, unusual. A coordinate patch X D to from D to R3 is a one-to-one regular mapping. I will explain all these of an open subset of an open subset D of R2 into R3. So I have to explain you what's regular. As usual, regularity means that the derivative map of x, so x star from the tangent space to D2 to tangent space of R3 is one-to-one. 1-to-1 at each point of D2. Okay. Each point P of D2. So let me draw you the picture. I have some open region here, D, this is R2. And we have a mapping, X is a mapping from R2 into R3. So I have R3 here. And its image here is a surface patch like this, probably. Okay. And if you are at a point here, P, then this is the point XP, the image of that point. Here, X is a function from R2 to R3. So you have two variables here. Let's say S and T. S and T, for example. Yeah, the U and V, UV. So it is X1 UV, X2 UV, and X3 UV. These are the X1, X2, and X3 coordinates, okay? The tangent map of this is 1-to-1, means what? At this point, I have two tangent vectors, right? This one and this one. Well, I have many, but two of them are these. So this is del X, del U, let's say. So these are the coordinates U and V in R2. This is del U at P, and this is del V at P. These are the directional derivatives at that point. And the derivative map sends these vectors to two vectors here, like this. So this is just X star of del U at P, and this is X star of del V at P. And this linear map, X star is 1-to-1, okay? That's the condition. This is the same condition for curves. There, what was regularity? Regularity means the tangent vector is not zero. But tangent vector there is just the tangent map, because you know tangent there, this function was from R to R3. So I had only one vector, and that linear map is not zero, means that tangent vector is not zero. In this case, I don't have two, I don't have one vector, I have infinitely many vectors. To check that the differential or derivative map is 1-to-1, you need to show that these two vectors, which are linearly independent here, are mapped to linearly independent vectors here, right? Just definition of DD, yes. Okay. As usual, sorry, I already said this. Okay, we will also ask ask that the coordinate patches to be proper maps. So what do we mean by this? What we mean by a proper map in this case is that x inverse from the image into D is also a continuous map. So in other words, we ask X to be a homeomorphism onto its image. In particular, X from D into R3 is a homeomorphism onto its image XD. So let's say this is our D, and via X is mapped to something like this, and this map from this region D into its image X of D is a homeomorphism. Okay, it has an inverse, and the inverse function is also continuous. Okay, that's the assumption for a coordinate patch. Okay, we assume that this coordinate patches, so-called coordinate patches, are so that they are homeomorphisms onto their images. Okay. Okay. Of course, X is a differentiable function. Otherwise, this doesn't make sense. So we already asked that X is a differentiable function, but we ask more than that, it's an homeomorphism onto its image. Okay. A surface in R3 is a subset M of R3 such that for each point P of M, there exists a proper patch in M whose image contains a neighborhood of P in M. So what's a surface? A surface in R3 is a subset of R3. It will be a subset of R3 with the following property. Whenever you pick a point here, okay, there should be a coordinate patch. You should be able to find some function defined on R on an open subset of R2, a function. This function should be proper. Its image should be inside M, and the image of D, whatever that is, it should contain a neighborhood of the point P. In other words, this point P should be inside this image, so X of D. It shouldn't be on the boundary, so there should be an open subset here, like this, okay? If this is the case, if you can do this, if you can find such a coordinate patch for each point of the subset M, we say that M is a surface in R3, okay? A differentiable function, so that its derivative is always one-to-one at all points, and moreover, it's a homeomorphism onto its image. Okay. Okay, the reason is that this D is an open subset of R2, and since this is a homeomorphism, right? Basically, this thing is the same as this one topologically, and so this piece is the same as this piece, and here in R2 I have coordinates. Okay, that's why this is like putting a coordinate system here, okay, on the surface. It may not be a global coordinate system, but a local coordinate system, okay? That's why it's called a coordinate patch. At each point, around each point, you have a coordinate patch. But, you know, they may be different coordinate patches. Okay, you may not find a global coordinate patch, and actually you shouldn't be able to find a global coordinate patch, because if it were, since by definition coordinate patch is a homeomorphism, the surface would be homeomorphic to an open set in R2. But not all surfaces are like that, right? Sphere is not homeomorphic to an open subset of R2. Okay. All right, so here is another definition. A surface, not definition, I am sorry. Yeah. I think it will be automatic. Yeah, but it's a good question. Okay, so I guess it should be a consequence of inverse function theorem or something. Okay, but yeah, I should think about it. All right, example is the following. The unit sphere gamma in not gamma, sigma in R3 defined by this. So points in R3 so that the sum of the coordinates is equal to 1. Okay, so it's a subset of R3. We claim that this is a surface. All right, so let's see if we can find such a coordinate patch around each point. Let's choose a point P1, P2, P3 in sigma on the sphere. Be a point on sigma. Since by the definition P1 squared, P2 squared, and P3 squared is equal to 1, at least one of them is non-zero. At least one of them is not 0. One Pi is not 0. Değil mi? 3 koordinat birden 0 olamaz. All right. First, assume that P3 is not 0. So the last coordinate is not 0. Indeed, let's assume P3 is positive. It may be negative too, but let's assume for the time being it is positive. So our point is a point on the northern hemisphere, right? X1, X2, X3. It is the unit sphere and the last coordinate is positive. Then the function x from D into R3 given by x uv, which is just uv 1 minus u squared minus v squared, where, well, D has to be an open set in R2, and here is D. U comma V in R2, so that U squared plus V squared is less than 1. This is an open set. It is actually the unit disk in R2, right? It is just inside this unit disk, right? This is this disk with radius 1. Is the unit open disk in R2. Okay. Well, you see that this coordinate is positive, right? I mean, square root of this expression since x u squared plus v squared is less than 1, this is a positive number, and here I take the positive square root. Therefore, hence what? X of P1, P2 is just what? P1, P2, and then 1 minus P1 squared minus P2 squared. But what is P1 minus squared, P2 minus squared? Well, from the definition of the sphere, 1 minus P1 squared minus P2 squared is just P3 squared. Its square root is plus or minus P3. Since we assume that P3 is positive, so this is just P3. P3. Since we assume that P3 is positive. Otherwise, I had to take this, negative one. So this is really the point P, okay? So I have found a function from an open set of R2 into the surface so that its image contains the point P. And it's yok. Open set alıyorum. Bunu open set alacağım ya. Eşitliği istemiyoruz çünkü o zaman sınırda olabilir. Sınırda da türev almak sıkıntılı. Yani çünkü sınır noktasına her yerden yaklaşamıyoruz. O yüzden open'larla çalışıyoruz. Okay, so we have to check that X is really a coordinate patch. Let's see if it is the case. Ne kadar zamanım var? Var daha. Okay. All right. Now we have to check a couple things. First, X is 1 to 1. Right? Because X should be a homeomorphism onto its image, therefore it has to be 1 to 1. Well, to see this, note that X inverse from XD back to X exists. Namely,
Hocam tahta kaldı yine.
özür dilerim. Okay. All right, so we need to first show that X is 1 to 1. So to do so, I need to, well, you can do several things, but the easiest one is to show that it has an inverse. And what is the inverse function in this case? So whenever I put a triple here, let's say P1, P2, P3, a point on the image of the surface patch, what should be the result? So X sends UV to UV something. Therefore, X inverse will send UV something to UV. So just the projection onto the first two coordinates. So X inverse is just P1, P2, right? Clearly, these two functions are inverses of each other. Okay, so this one and this one are the identity functions on this one is defined on x of d and d respectively. Değil mi? Bu iki fonksiyonu kompoze ederseniz her ikisi de identity fonksiyonu. Birisi d'nin, birisi x of d'nin. Right? Both of them are identity functions. If you go with first by x and then x inverse, right? Let me do one of them. So P1, P2, P3. What is this? This is x of x1 of P1, P2, P3. But this is just P1 and P2. All right. What is x of P1, P2? Well, this is P1, P2, and then 1 minus P1 squared, P2 squared. Well, what is this? Well, it is P3. Why is that? Because I am on the northern hemisphere, and this point is on the sphere, right? So P3 is the positive square root of 1 minus P1 squared minus P2 squared. Therefore, this is just P3. So what you get is then this point is just mapped to itself, right? So this implies that x composition x inverse is the identity function of x of d. İsterseniz şöyle yazayım. So x composition x inverse no. Yok, doğruydu. This is the identity function of x of d. And similarly, x inverse composition x of uv, what is this? Well, this is just x inverse of x of uv. X of uv is just uv and then 1 minus u squared v squared. But what is x inverse of this? Well, it is just projection onto the first two coordinates, which is just this. Hence, and thus, x inverse composition x is just identity function of d. Okay, so they are inverses of each other. This means what? This means and x inverse is also continuous, right? So this shows x is 1 to 1, 1 to 1, and onto its image xd, which is just the open subset of the sphere, which is this subset x1, x2, x3 on the sphere such that the third coordinate is positive. So the whole northern hemisphere, okay, its image is the northern hemisphere. What else? X is proper. Well, this is true. Why is that? Because X inverse is also continuous. X inverse is also continuous, right? What is this X inverse? X inverse is just projection onto the first two coordinates, right? Projection function is always continuous. Therefore, this is a continuous function. Since X is continuous and it has a continuous inverse, X is a homeomorphism onto its image. Is also continuous, so that X from D into onto XD, which is a subset of sigma, is a homeomorphism. Okay. Okay. The third condition is that X is regular. Regular means what? The derivative map should be 1-to-1. Okay. So we need to take the derivative of this function. What is this function? It's a function from an open subset of R2 into R3. And here are the coordinates. To find the X star, we need to compute its Jacobian. So this is just is given by the matrix multiplication with the Jacobian matrix J, right? What is the derivative map of this? It's given by matrix multiplication by the Jacobian of this function. So it is just, I look at the coordinates of this function. Let's say this is the x1 coordinate, x2 coordinate, and x3 coordinate. And then it will be just del of x1, del u, del of x1, del v, and then del of x2 del u, del of x2 del v, and del of x3 del u, del of x3 del v. And if you do the computation, what are the derivatives of these functions with respect to u and v? So this will give me 1 and then 0. The second one is 0 and then 1. And x and v, y coordinates of this. Okay, let me. Sorry, u and v derivatives of this is what? Minus 2u divided by 2 times square root. So it is just minus u times 1 minus u squared v squared. And this is just minus v times 1 minus u squared v squared. So it is this. And you see that this map from R2 to R3, right, is always 1-to-1 because it has rank 2, right? It has rank 2. So Let me write that down. Clearly, Jacobian has rank 2 at all points. UV of D, so that the derivative map X star is 1-to-1 at all points. Okay. What about other points? Here, we did all these computations at a point where the last coordinate of the point P is positive, right? So I took first an arbitrary point, but then I assumed that the last coordinate is positive, and I did my computation under that assumption. What about, the other points? This point could be here or could be here, right? On the equator. Then I need to find other coordinate patches. For the point where P3 is negative, life is still easy. So, okay, if P is like this, so that P3 is negative, then we could choose the coordinate patch as follows. X of UV, again the same function defined on the same D, but the coordinate functions are a little bit changed. So UV here, and since the last coordinate is negative, I take the negative square root, okay? What about a point which is on the equator? If it is on the equator, then it means the last coordinate is 0, right? If P3 is 0, in other words, the point is on the equator, then either P1 or P2 are non-zero, right? Because 3 coordinates altogether cannot be 0. If this coordinate is 0, one of them should be non-zero. And then you just repeat the same thing for the other cases. For example, if, let's say, P1 is not 0 and suppose it is positive, then we may choose X from D into R3 as follows, as X of UV. Well, okay, so this will be just 1 minus U squared minus V squared, and I take positive square root since P1 is positive, and then UV here, okay? So you would choose this one. And I guess you understand the game, right? How it will. Okay. And actually, if you look at all these functions, they are nothing but projections onto the coordinate planes, right? Note that all the coordinate functions, coordinate patches. Patch. Nasıl yazılıyor? Patch. Önce C mi? Sonra T. All the coordinate patches are nothing but actually inverse of coordinate patches are nothing but the projections or inverse of the projections. Inverse are the inverses of projection functions onto the coordinate planes. Namely, you see, here is my sphere, okay? There are 3 axes like this and 3 coordinate planes, right? X1, X2 plane, X2, X3 plane, and X1, X3 plane. And all these coordinate patches are just inverses of the projection functions. If you are at a point like this, then you may consider projection onto the XY plane. So here is this point, and that gives a coordinate patch defined on this unit disk, which is in the plane x1, x2. And in that case, I would call this U and V, right? So this point is just, let's say, UV, and this point P is UV 1 minus U squared minus V squared. Of course, that wouldn't give a coordinate patch for a point which is on the equator. If you are at a point which is on the equator, let's say like this, suppose you are at this point, your P is here, then you would choose projection onto the x1, x3 plane. So you would get, this disk here in the x1, x3 plane, and this point would map to a point on this disk. So in that case, I would call this one as U, this one as V, and this point in that disk is just the point UV. And what about this one? It is just, X1 is just U, X3 is V. What about X2? It is 1 minus U squared minus V squared. Is it plus or negative? Well, since I am on the positive side of the x2 axis, so the second coordinate has to be positive. So I would choose projection this way, and the coordinate patch is just the inverse of that projection. Değil mi? Her seferinde koordinat plane'lerinden birine projection size bir coordinate patch veriyor. Okay, so let me stop here. We will actually see that this always works, okay? If you have a surface in R3, nice surface, then projections onto one of the planes, 3 planes, would always give you a coordinate patch, okay? That's a consequence of inverse function theorem. Maybe next time I may talk about that. All right, let's stop.